So now let's take a very simple real world example and understand how digital logic circuits can be designed. Right? It's a very simple thing. Again, any one of you who has gone to a bank locker, right, where you store your precious items, gold or certificates or anything that is important to you. So this is how a bank locker looks like, right? So if you notice, a bank locker has two keys that need to be inserted. One key is what the bank manager has. The other key is what you have as the customer. Here C represents the customer, right? So the bank manager inserts his or her key. The customer inserts his key. Now when both of these keys are valid, only then the locker opens. Okay, that's very important logic, because this logic is designed for security. The bank manager alone should not be able to operate the locker or open the locker. The customer alone, without the permission of the manager, cannot open the locker. Okay, this is the real world business problem, or a real world problem that can be addressed using simple digital logic design, right? So this problem is called as operating a bank locker, right? Many of you may have gone to lockers with your parents or with your family members and have seen something like this. Now, if you think logically, look at this. Let's represent a digital logic circuit as a simple box here. Okay, we'll see how the logic itself works. The digital logic circuit has two inputs. One is the manager key valid or not? Is the customer's key valid or not? Right? So the inputs here are binary. Remember, digital circuits are all binary as of today, right? So the manager key, if it is valid, this will send a signal of 1. If it is invalid, it will send a signal of 0. Now the logic here is, if both the manager key is valid and the customer key is valid, then the locker opens. Okay. Today, most lockers are designed as a combination of electronics and mechanical systems, because there is a physical lock that has to be put in place, right? Again, depending on the bank you are using, more advanced banks have digital locks. Some banks have just physical locks, depending on the system. But imagine if you were to digitize this system, the logic is very simple. The logic is, if both the manager key and the customer key are valid, then the key that they insert, if they both are valid, then only it should open, otherwise it should not open. That's the simple logic behind it. Now, if you were to design a digital logic circuit for this, first you should understand the actual real world use case, just the way we have done till now, right? The business logic we should understand first. The real world operation. What is the logic behind it? We should first understand it. Then remember that the bank manager inserts a key here. This is the manager and this is the customer, right? So they insert a physical key and probably rotate it, or if it's a card, they just put in the card. What happens is, when they enter something like this, when they place a key, right? Any electromechanical system which is not digital is called as an analog system. Your key is also an analog system because it's a mechanical system, right? So the moment they insert a key and rotate it, whether that key is valid or not is determined using a special circuit called as analog to digital circuit, often referred to as ADC. Probably the analog to digital circuit will see the actual shape of the key itself, right? Or the shape of the teeth of the key. You have a key like this, right? It has some teeth like this, right? It looks at the shape of the teeth of the key and says, yes, this is valid or this is not valid. So there is an electromechanical system called as analog to digital circuit, which actually takes in the key and returns a digital value of 1 or 0. It returns 1 if the key is valid, 0 otherwise, right? So you have an analog to digital system that you have to design. Again, this is typically designed by electronics and mechanical engineers. Then you have to understand the truth table or the logic behind it. Again, truth tables is a concept that we have studied in discrete mathematics when we learned Boolean logic, right? So I'm assuming you've gone through that concepts and you understand the basics of Boolean logic and truth tables. And how does a truth table look like? It has all the possible values of the binary variables we have and what is the output that we want to generate. Okay, so M can be either 0 or 1. M basically represents whether the manager key is valid or not. C represents whether the customer's key is valid or not. So this has two values, 0 or 1. Now based on various combinations, because M can take two values, C can take two values, there are a total of 4 possible values, 2 into 2, right? So for each of these combinations, what should be the logic for the output or the open logic? You can read OP as open. So OP equals to 0 means don't open, OP equals to 1 means open. The simple logic here is, if this says not valid, it should not open. If the customer key is valid but the manager key is not valid, it should not open. If the manager key is valid but customer key is not valid, it should not open. Only when both the keys are valid that the locker should open. Very simple logic, right? So this is what is often referred to as a truth table. Then you represent the truth table using a Boolean expression. Again, we have studied Boolean expressions and Boolean algebra when we learned this concept in discrete mathematics. So I'm assuming you have covered that. So we can write this whole truth table into a simple mathematical expression and say OP, or the open, is nothing but M and C. If you're writing it in a programming language like C, you say M logical and C, right? This is the programming language way of writing things. This is the Boolean algebra way of writing it. Again, remember that AND is written as a product. So M and C is M multiplied by C, also written as just MC. M or C, right? Remember, M or C in Boolean algebra is written as M plus C, right? I'm assuming you know this terminology, right? If you don't know, please watch the videos that we have on discrete mathematics, especially Boolean logic, and all this will become clear, right? Next, so once we have this mathematical expression, we will start designing the digital logic circuit for this. Remember, this is how programmers write logic. This is how math guys write logic. The digital circuit designers, the electronic guys, represent the same thing in a slightly different way. This notation or this representation is how electronics engineers or digital engineers represent it. Okay, remember, this is just the programming way of looking at it. This is the mathematical way of looking at it. This is the circuit or electronics way of looking at it. All three of them mean the same thing. So whenever you see a circuit like this where you have M, C, and you have this circuit, this means what this outputs is nothing but the logical AND of M and C. Again, logical AND is represented using this umbrella shaped structure. Logical OR is represented using this structure. Look at this. This is how logical OR is represented. Remember, mathematically OR, if you have A and B as inputs, the output is A plus B. Similarly, NOT is represented using this. Okay, so NOT is often represented just using this circle, or it's also called as a bubble. This means it's a NOT. NAND is nothing but AND. Look at this. This is AND, right? This shape is AND followed by a bubble, which means it is NAND. Again, we learnt about AND, OR, NAND, NOR when we learnt Boolean algebra. It's the same concept here, except that now we are trying to translate Boolean logic and Boolean expressions into hardware circuits. Okay, so this is how you see in many circuit diagrams. This is the electronic circuit way of representing the same thing. Now similarly, NOR, note that this is OR. This part is OR, same as OR. Since you put this bubble here, it becomes NOT. So NOT of OR is NOR. Right? Very simple. Look at this. This is OR with a bar on top, basically means it's a NOR. This is AB with a bar on top. AB is AND. The NOT of it is NAND. Right? So in any electronic circuit, if you see this diagram, this represents that it's an AND gate. They call these as gates or digital gates. Again, you might encounter this term called digital gates. Right? So these are often called as digital gates, and that's the electronics terminology. Again, remember, this is what programmers use, this is what math guys use, this is what electronics and circuit designers use. All mean the same thing fundamentally. It's just a different symbolic representation of it. Right? Now, your question here is, okay, now I got the logic. I also understood how to represent it. This is how we have to represent it. But how do I actually physically implement it? So you can just Google search for AND gate. So you can just search for AND gate, chip for AND gate. If you just Google search for it, you get a Wikipedia link which says that there is this chip called, or an integrated circuit chip called 7408. Again, every chip has a unique number associated with it. So this chip number 7408 is basically it looks like this. Again, this is nothing but 7408. Look at this. 74. This LS and all talks about some technology they are using, but effectively this is 7408. It's a small chip. It costs, I think, 10 or 15 rupees, or about 20 cents in the US dollars. It's a very simple chip, and these are called as pins to the chip. Okay, these are called pins. The actual physical logic itself is here inside this chip. You can put this on a breadboard. You can also put this on an electronic circuit and connect the wires. So this is how the chip looks physically. This is called the internal diagram of how everything works. Okay, look at this. So if you notice, this has this small shape here, right? So which means, again, look at it. To understand whether this side of the chip or this side of the chip, they put this very simple logic here. So let me erase this and show it to you clearly. Okay, so if you notice, this says that, so this side and this side are the same. The first pin here is here. The second pin, third pin, fourth, fifth, sixth, seventh. If you notice, there are 7 pins this side. There are 7 pins on the other side also. To make this circuit work, you have to connect this pin, the pin that is there on that side, to +5 volts. And this is ground, right? So in any electronic circuit, you know that there is power supply that you have to give. This is like a positive of the 5-volt battery, and this is the ground, the negative, right? So the moment you connect, so VCC in electronics basically means you connect it to plus the positive side of your battery, this to the negative side, right? So again, I'm not going too deep into electronics. I'm just trying to give you a high level overview here, right? So you connect your 5 volts and ground, then this chip becomes active. When the chip becomes active, you can now start. Suppose if you connect your M here, remember your analog to digital circuit translates your whatever you have inserted into the key, it translates that into a digital signal, 1 or 0, 1 for valid key, 0 for invalid key. That output, the digital output, if you insert M here and if you insert C here, right, because it converts into digital, right? So which means this will send 1, digital 1, and this, if this sends digital 1, the output can be obtained by connecting to the third pin here. So you connect your M here, the output that you get from ADC, you connect your C here, this is where you get your output. Look at this, you can actually put this on a breadboard. Again, if you open any circuit board in any electronics, you'll see lots of chips like this, right? This is a very, very simple, very, very cheap chip that you can use. Now, how does the whole architecture itself look like? Let me explain you at a broad, because we have all the pieces now. Look at it. First, we understood the logic, the business use case logic. Then we had analog to digital converters. Again, this is something that is not important for computer science engineers as much, because it is electronics and mechanical engineers who design it. Then we understood the truth table. We converted the truth table to a Boolean expression. We understood what digital circuits can be used. We even Google searched and found out a specific chip that we can use. So now the whole logic will work as follows. So the physical locker, the manager inserts the key, the customer inserts the key. As soon as the manager inserts, there is an analog to digital circuit which says if the key is valid, it will generate 1 or else it will generate 0. Similarly, for the customer key, there is also another analog to digital circuit very similar to the previous one, which generates valid or invalid. Now these two values, look at this, this C value, this is C, this is manager, right? The Boolean representation, whether these keys are valid or not, go into chip pin 12, pin 13 in 7408 chip. Again, each chip has a unique number. Nobody remembers these numbers by heart. You Google search for it in the real world. Then it takes this input, it takes this input. Look at this. This gate shows that it's an AND gate. So this chip has 4 AND gates that you can use. In our use case, we only require 1 AND gate. So the other 3 AND gates will just sit idle, will not do anything. So then the output from this is available in chip 11. Sorry, in pin 11. In pin 11, you get the output. So if these two are valid, you get a valid output. If any one of them is invalid, you get an invalid output. Now you take the digital output, then you have another electromechanical component called as digital to analog circuit, which takes a digital signal and converts it into an analog or a mechanical or electromechanical system. This electromechanical system will either open the locker or not open the locker. So again, remember that ADCs and DACs are what mechanical and electrical engineers or electronics engineers design. The digital circuit, it's electronics engineers and computer science engineers who are responsible for it. Right? This is how, when you have to design, again, I've taken a very simple example. I'll cover more examples, more complex examples a little later, but I wanted to start with a very simple real world example. And here are the steps which are very important that you follow in designing a real world simple circuit.